physical chemistry from UC Irvine. And finally, he completed his training as a postdoc at Lawrence Berkeley National Lab. And in 2011, he joined HSU and is currently an associate professor at our department. All right, Chris, floor is yours.
Okay, thank you, George. I have the pleasure of introducing George next week during seminar. Okay, I'm gonna go ahead and do a screen share. You all can tell me if, so let's see, I'm gonna move all my windows out of the way. So can everybody see everything okay? Beautiful, okay. And I think I can even grab a little laser pointer here. Okay, wonderful. Okay, so thanks for coming to my talk, everyone. So I gave a similar talk as this to the department in the fall 19 semester, which was just one semester before the pandemic. And we were sitting on a mountain of data that I hadn't yet processed. And of course, we went into lockdown. And so I was able to work through some of this data. And so now what I'm going to present for you are our quantitative investigations. So the last time I presented this work, it was qualitative. And so we're looking at the adsorption and desorption of acetone on titanium 4 oxide. So just briefly to tell you a little bit about Earth's atmosphere, we live and exist in the planetary boundary layer. So that's the lowermost sliver of the atmosphere. And so this is really, like I said, it's an extremely short little area compared to the full height of the atmosphere, okay? And so why that's important is because we consider now how air circulates around the globe. And in the planetary boundary layer and in the troposphere, this is quite fast. So as you can see from the figure here, in the northern hemisphere mid-latitudes, air can circulate around the globe in a period of 1 or 2 weeks. It's very fast. And if we want to move air from the bottom of the atmosphere up to the top, or even exchange the northern hemisphere with the southern hemisphere, that can be quite slow. But all of the same, this is kind of intended to show you that human activity is not isolated to any one corner of the globe. If we wait long enough, the air, it will become well mixed all over the planet, okay? So if we look at our composition, the atmosphere is mostly nitrogen and oxygen, along with some trace gases, all right? So, and just to give you some background, so we're talking the same language, we use this volumetric mixing ratio in atmospheric chemistry. So for example, 1 part per million, you might be used to that as a milligram per liter for solutions. But in atmospheric chemistry, we call that a part per million by volume. And under the ideal gas approximation, number of moles is directly proportional to the volume. So if I have 1 out of 1 million molecules, I have a concentration of 1 part per million. Okay, and so sometimes you'll see that ppmv, and sometimes you'll just see ppm. In this talk and in atmospheric chemistry, we're referring to the volumetric mixing ratio. And so if I zoom in on these trace gases, here we note carbon dioxide at, the figure says 400, but it's actually around 415, 420 or so. And just the 2 years ago that I made this slide, it's changed by that much. And so methane, also about 1.8 part per million. So we know these as greenhouse gases, okay? But that's not what the story is about today. What I want to focus on today are the very small concentrations. So our VOC, which is volatile organic compound, those exist in the part per billion range. Ozone, a powerful atmospheric oxidant, It's quite dynamic, but it's roughly 40 parts per billion planet-wide. And the hydroxyl radical, a very important atmospheric oxidizer, exists in the part per trillion. So these are very small concentrations. However, VOC and atmospheric oxidants are really important for air pollution in Earth's atmosphere. Okay, so there's also particles in the atmosphere. We often kind of interchangeably call these particles or aerosol. So by definition, aerosol is a stable suspension of a solid particle or a liquid droplet in the gas phase. And here are all the most common types of particles. So we start with cloud droplets. So these are quite humongous, 100 micron in diameter on average or so. And then our next biggest goes all the way down to a typical sea salt particle, about 2.5 micron or so. And these sea salt particles are little aqueous beakers floating around in the atmosphere. So they're loaded with salt as well as water. So they're typically saturated solutions. And then we can see dust particles. So these originate from continental crust. So wind action picking up dust on the ground, right? Smoke particles get even smaller at about 1 micron. So a typical smog particle, which is formed secondarily through chemistry, can get even smaller, about 500 nanometers. Diesel particles are even smaller than that. And then on this scale, a typical molecule, we can't see it based on the magnification here. Okay, and so these are just a range of sizes. So particles can exist. So, you know, not all dust particles have to be 2 micron. They can be smaller, but this is just a typical size. Okay. So I have a fantastic movie that I'd like to play for you all. And this comes from 2017, so it's a little bit older, but it's still really great. I could stare at this thing all day. And so it's about 2 minutes long, and there's some narration that goes along with it, which is, it's a little cheesy, but I think the narrator does a really good job pointing out what I want you to learn from this video. And particularly, I want you to note the false color scales that you see at the bottom for dust, sea salt, and smoke, as well as the date. Okay, so let's watch this video.
How can you see the atmosphere? The answer is blowing in the wind. Tiny particles known as aerosols are carried by the air around the globe. This visualization uses data from NASA satellites combined with our knowledge of physics and meteorology to track 3 aerosols: dust, smoke, and sea salt. Sea salt, shown here in blue, is picked up by winds passing over the ocean. As tropical storms and hurricanes form, the salt particles are concentrated into the spiraling shape we all recognize. With their movements, we can follow the formation of Hurricane Irma and see the dust from the Sahara, shown in tan, get washed out of the storm center by the rain. Advances in computing speed allow scientists to include more details of these physical processes in their simulations of how the aerosols interact with the storm system. The increased resolution of the computer simulation is apparent in fine details like the hurricane bands spiraling counterclockwise. Computer simulations let us see how different processes fit together and evolve as a system. By using mathematical models to represent nature, we can separate the system into component parts and better understand the underlying physics of each. Today's research improves next year's weather forecasting ability. Hurricane Ophelia was very unusual. It headed northeast, pulling in Saharan dust and smoke from wildfires in Portugal, carrying both to Ireland and the UK. This aerosol interaction was very different from other storms of the season. As computing speed continues to increase, scientists will be able to bring more scientific details into the simulations, giving us a deeper understanding of our home planet.
Okay, so that is such a cool simulation. I have probably watched it 1,000 times, and I will watch it 1,000 more times. It is so interesting to see how the smoke and dust and sea salt move all over the globe, particularly how all of those different types of particles interact and mix. And also you notice the narrator talked about adding more details. Well, one of those details that I think would be really cool would be volatile organic compounds, to see how a VOC can be transported around the globe and how they interact with those dust particles. Okay, so now you notice from the title that I'm interested in titanium oxide, titanium 4 oxide. And it's worthwhile to note that there is not a whole lot of titanium circulating around. It's quite low in its abundance. However, it is by far one of the more reactive components of dust particles in particular. Okay, and so I find that interesting because as a means of picking a place to start, well, I choose to pick the most reactive thing to start with, okay? And so you can also kind of see some of these other images of dust storms. So this picture right here is actually on the Baja Peninsula. The picture is got north, or it's upside down, right? So you can see the Pacific Ocean. We're normally used to seeing that on the left. So this is farmland, where you can see a large dust storm pushing out over the ocean. Or similarly, you can see this large dust storm interacting with Europe. And so what I'm interested in is how these particles pick up things in the atmosphere and move that stuff around, okay? So as I said, titanium isn't particularly highly abundant, but it is very reactive. So it has notable photochemistry, which can occur under wavelengths we see in planet Earth. And it's also a really good catalyst, okay? And furthermore, it's been studied extensively. So that also makes it a good place to start, as there's a lot of literature available to support our observations, okay? So here is our story here. What I'm doing is we're looking at a model VOC, and we've chosen acetone to start. It's not my favorite compound by any means, but it's a good model compound to start with. And so what I'm interested in, and how is a compound like this or other volatiles able to get picked up by some aerosol particle and perhaps form some organic layer and then go on to be further modified by light or humidity or oxidants. So hypothesis number one, acetone or other VOC will stick to the surface of aerosol particles, okay? And so we also hypothesize this sticking will be irreversible, meaning that it will be chemisorbed, okay? And so it will be able to be transported long distances that way. And as this VOC, as it gets taken up onto the surface, that it will become this organic layer that will then alter aerosol particle properties, because now the surface of this particle is some organic layer as opposed to this inorganic core. And so the way that it interacts with the environment will be different if it's got this organic shell around it, okay? So here's how we're going to test the hypothesis. So we want to gather quantitative information, such as rate constants or uptake coefficients, and I'll talk about that in more detail soon. And then we want to use that quantitative information to assess if this VOC sticking is important. And then to assess the validity of this organic layer, we want to look for evidence of a chemical reaction on the surface of our particle, okay? So as I mentioned, there's lots and lots of literature out there, even particularly lots of literature out there on acetone and titanium oxide, okay? So that's again why we've chosen to start with this system. But a lot of these studies are done in what I would call highly idealized situations where perhaps they're looking at this under vacuum or under very cold temperatures. And of course, cold temperatures are relevant to the atmosphere, certainly. But my what we want to do here is look at this under conditions that might be more applicable to the atmosphere. And for us, that's doing things around room temperature and room pressure. Okay, just that simple modification of looking at things at roughly 1 atmosphere of pressure, as it turns out, is novel. Also, a lot of researchers elect to go after the uptake coefficient. And so the uptake coefficient is defined as the number of effective collisions that lead to sticking. So for example, if I have 100 molecules and all 100 of them collide and stick, then it would be an uptake coefficient of 1. Whereas if, let's say, only 1 out of 100 of those collisions result into a molecule sticking, it would be an uptake coefficient of 0.01 or 1%. So what we're going after is the adsorption rate constant. And furthermore, we're going after this because you notice if I'm interested in the kinetics here, if I'm interested in the loss of VOC over time, so dVOC dt, I can put this in terms of the first order adsorption rate constant or in terms of the uptake coefficient, but this requires me to know this SS parameter. That's the solid surface area at the solid gas interface. And more on that later on in the talk, but this is a very difficult parameter to go after, okay? So we're choosing to go after the adsorption rate constant for our quantitative studies, okay? And so just to remind you all, so when molecules land and stick on surfaces, they stick on active sites. And active sites occur at what we call kinks, ledges, or steps. So these are all scientific technical terms: ledges, kinks, terraces, and steps, okay? And so where we see these ledges and kinks and so on, these are great places for a molecule to stick. Also, where a unit cell might be incomplete because it's residing at the surface, right? If you think about, some large number of unit cells expanding on, we normally just think they go on and on and on forever, but it has to stop somewhere. And so at the interface, those unit cells will be incomplete. And so those are great places for adsorption to occur as well. Okay, so I'm going to get into the methods now that we are using, and I'd like to give you some background on those methods. So we're using the diffuse reflectance infrared Fourier transform spectroscopy technique. That is a mouthful. So we call this the DRIFFUSE technique. And as I'm fond of telling students, if your technique has a really cool acronym, you're doing something modern and cool. So DRIFFUSE is a cool acronym. So we recall the law of reflection. So if we have an atomically smooth surface, let's say, then our angle of reflection will match our angle of incidence. And of course, it doesn't have to be perfectly atomically smooth to observe this. For example, in this picture right here, taken early in the morning, perhaps we've seen something like this, right? Where we get this beautiful specular reflection off of a calm body of water, okay? And as we might know anecdotally, if the wind picks up and the water gets a little bit more choppy, we don't have this beautiful specular mirror image any longer. We get what's called diffuse reflection, okay? And so this is what we take advantage of in our technique. We're not trying to create some optically smooth surface. We're just going to take our surface and all of its imperfections as is. Okay, so here is a nice schematic of our apparatus. So this is our DRIFFUSE cell. It is parked inside the compartment of a commercial FTIR, Fourier transform infrared spectrometer, and that's the same type of instrument you used in OChem. Okay, so but we have this custom-made cell that can reside in the IR cell. And it's got a convoluted set of optics where an IR beam is first bounced off of one mirror. It goes through our transparent, our infrared transparent zinc selenide optics. We use zinc selenide because it's chemically inert to oxidants and it doesn't interact with water particularly strong. And so we'll get this diffuse reflectance right off of our sample. And these elliptical mirrors will then focus that beam on another mirror and send it off to the detector. What makes this sample cell special is that we have the ability to heat the sample. We have the ability to cool the sample. I could actually pump vacuum on this chamber. So these optics are outfitted with O-rings, and they do hold a vacuum quite well. Or, as noted, we could flow atmospheric gases over the surface of our particles. Okay, and you can see that here in this picture. This is the entrance, gases going into the cell, and this green tube right here is gases coming out of the cell. So this is always, in our experiment, open to the atmosphere. So this long line goes off to the hood, and it's open to the atmosphere so that we can maintain atmospheric pressure inside our drift cell, which is a goal to study this chemistry at atmospheric pressure. Okay. So this is a more detailed look at our manifold. This lovely schematic was drawn by Emmy McCain, one of my students who graduated in 2018. So she hand drew this picture and then imported it into Photoshop, which is just so neat. A really talented student. She did really good science too. So what I want to point out here is this syringe pump. So this is the novel way that we're introducing organics into the gas phase. So this is a typical syringe pump that you can load we load a gas tight syringe, and it goes into a GC septum at the end of this T right here. And we program the syringe pump to pump organics at a known flow rate in microliters per hour. So in this case, acetone. And you can see it's got this really long mixing tube. And what's not pictured here, what's difficult to see, there's a nitrogen line that comes in and connects to this mixing tube. So as we are injecting acetone into this mixing tube, liquid acetone, we have a large flow of nitrogen that sweeps it all out. And for now, we just assume all of that acetone gets evaporated and goes off into the gas phase. And just using simple stoichiometry, we can calculate how much acetone we put in the gas phase, of course, assuming that it all evaporates. That's one of our assumptions for now. Okay, and so then this VOC, I can now mix it with other gases such as nitrogen and oxygen, so I can create a synthetic atmosphere. And then I can flow all of that into my drift cell. Okay. And then here's a picture of the bench. So this is the FTIR. The drift cell is inside that gray box. Computers for data acquisition, and then everything you see in this picture is housed in this manifold right here. Okay, and I'm delighted to report this was all built by undergraduate students. So I was in the lab helping them build it, but I would say the undergrads did probably 90% of the manual labor, plumbing up all of these lines and organizing where each flow should go. So this was a huge amount of work, just building this apparatus in the first place. So let's talk about spectroscopy. So if you recall, absorbance is the negative log of transmittance. And of course, transmittance is the ratio of a beam intensity transmitting through a sample ratioed to some background. Okay. So now you notice that we have actually the incident beam I0. And of course, because our optics, and this could be a cuvette, this could be my drift cell, whatever you would use to hold your molecules, it's going to have diffuse reflectance, right? There's going to be all of these scattering events at the surface, okay? But if we've done a careful job doing our spectroscopy, ratioing our sample to our background, then we ratio out all of those scattering events. So if you recall in your Chem 109, when you have to put the cuvette into the spectrometer in this very precise way, it's because you want to normalize out all of these scattering events. So the only thing that you see is the ratio of the intensity exiting the sample compared to the ratio of intensity exiting some background, which will be, the same container that you used without your absorbing molecules. Okay, and so I'll remind you, absorbance can also be given by Beer's law, which is the molar absorptivity coefficient, which we also sometimes call the absorption cross section, multiplied by concentration, multiplied by path length. Okay, so this is what I call survey spectra in my lab. And so if we wanted to know the appearance and position of functional groups, we would do a survey spectrum. Now, if we wanted to do chemistry, we use what's called difference spectroscopy, or as I like to call it, an action spectra. And in an action spectra, our sample is our background. Okay, so we don't have a blank in these experiments. We're loading up our sample into the drift cell or cuvette or whatever you would use, right? And now, and of course, we then record a single beam background spectrum of that sample. And then now we do something to it, right? We do chemistry in some way. And through time, we take successive measurements. And so if anything happens to our sample between condition 1 and condition 2, our absorption spectra will only reflect those changes. And so, for example, if we see the appearance of a new functional group, we'll have a positive peak. If we see the disappearance of a functional group, we'll see a negative peak. So this is a very cool technique for doing chemistry in situ. Okay, so here's some metadata. So these are our collection parameters. So we use 500 single beam scans averaged into one spectra. It takes about 5 minutes. And we do that because we're looking at an impressively small amount of material. So we have to average a large number of single beam spectra to even see anything. So the Kabulka-Monk algorithm is used when we want to do qualitative studies. And so I don't want to spend a whole lot of time talking about the theory of Kabulka-Monk. It can be kind of thought of the surface equivalence of Beer's law, but it's not very good at being quantitative. However, it is really good at making lovely flat baselines so that we can see a survey spectra nice and resolved. We're going to use the absorbance algorithm for quantitative spectra. Okay, so we store all solid reagents in an oven after copiously grinding them so that they're a nice small particle size. So we distill acetone to remove any volatile impurities, and it's stored in a dry box when we're not using it. All of our gas reagents are ultra high purity, which is 99.9999% pure. If you're good at math, you'll note that that is actually still 10 part per million, or excuse me, 100 part per million impurities, but it's the best we can do. And all reactions are carried out in situ in the drift cell, and we have not done any cooling. So our drift cell is about 27 degrees. It's warm in there because of the electronics of the spectrometer. Okay. So the first, one of the first things we did was get an image of these particles. This image was done by one of my students, Jesus, and we published this work in the IDFS paper here. So this is what a typical sample holder looks like. We have these little metal sample cups that are about 1 centimeter or so in diameter, and we don't press these like a pellet. We try to very gingerly put the gently put the powder in there because we want it to be fluffy. We want the gas phase to be able to interact with these particles. Okay, and so here you can see what those particles look like, and they are fluffy. There's space between the particles, and that's what we want. And you can also see these particles are on the small side. So we noted that representative mineral dust is about 2 micron. And our particles are a bit smaller than that, but still within a reasonable size for atmospheric relevance. Okay, and so let's talk a little bit about titanium oxide surface chemistry. So this sentence right here describes my entire PhD thesis really well. There's water on everything. Even some of the most hydrophobic stuff on planet Earth still is not far away from a water molecule. So done. 4 years of PhD graduate work described in one sentence. As it were, titanium-4 is a fantastic Lewis acid. So it's really good at attracting electrons, okay? And so because of that, it will undergo this chemistry that you can see right here, where it will deprotonate water, and you get what we call a dangling hydroxide, okay? And on the surface of most oxides, silicon oxide, aluminum oxide, iron oxide, and so forth, at the interface where you have an incomplete lattice or ledges, kinks, etc., we expect there to be dangling hydroxides in most conditions in planet Earth, okay? So this is some of our first spectra. So here, and I'm going to describe in a little more detail how we do this. But we have now, we're looking at flowing about 10 part per million by volume of gas phase acetone over the surface, okay? And we record a spectra after that happens. Here we've done this in the Kabuka-Monk algorithm, which, as you can see, makes a beautiful flat baseline, okay? And so there's a couple features to point out. For one, we see all the features associated with acetone, which I'll summarize on the next slide. What's really interesting about this technique, as I mentioned, we can see the simultaneous appearance of positive peaks, meaning we added something to the surface, as well as negative peaks, meaning something was removed from the surface or even something was modified, all right? So we notice that we've got this large negative peak at 3670 wave number. So that is an OH stretch that is associated with non-hydrogen bonding interactions, okay? So when we view OH stretches, let's say in bulk liquid water, we view like it's a broad stretch that occurs between 3,400 to 3,000. Okay, so these dangling hydroxides, they're not strongly hydrogen bonded with any other waters. So it's going to be a nice sharp peak, and it's going to occur at a higher wave number. And this is consistent with observations of others. So as we're flowing our acetone over, we postulate that the acetone is perturbing or displacing some of those dangling hydroxides. We can't say with definite confidence that it's just removing them, but we can say that it's perturbing them, that it is interacting with this dangling hydroxide in some kind of interesting way. Okay, and so we also suspect our acetone is going to interact with titanium in this way, right? The lone pairs from the oxygen are going to interact with the titanium. And so here we can see all the features associated with acetone. So here's the large carbonyl stretch, which is consistent with others. We can also see a very tiny set of methyl stretches. They have a very low cross section, so they're very small peaks. And we also see peaks associated with what I like to call the aliphatic region. So these are the methyl rocking motions, okay? And these are all consistent with what is viewed in literature. So this gives us good confidence that our acetone is sticking to the surface, particularly that we see this negative dangling hydroxide peak at the same time that we see positive peaks associated with acetone. Okay, so we're going to get into now describing the quantitative studies. And I'll remind you, the first order process. So if we go through this math right here, a first order process gives you an exponential decay. So that's the important thing to note here, e to the negative kt. All right. And based on the conditions we're using, we're assuming a Langmuir type adsorption under pseudo first order conditions. And those pseudo first order conditions are that our acetone in the gas phase is in such a large concentration that we're not worried about it. What is driving our kinetics is the number of available surface sites. So that's this M surface, our metal surface sites. And then our adsorbed phase. So AD stands for our adsorbed phase. So K-ad is the rate constant for adsorption, and K-des is our rate constant for desorption. Okay, so based on these conditions, right, we have a 5 cubic centimeter volume and we're flowing 50 cubic centimeters per minute. So this is how we know that this is pseudo first order, because the concentration of our gases going in is going to be the concentration of gases coming out, because this cell is constantly refreshed, okay? And so as our IR beam comes in here, we're actually not going to see anything in the gas phase, because the path length of our adsorbed phase is much, much longer than our path length in the gas phase. That's because of all these random diffuse reflectance events, okay? And so when we apply our Beer's law, we note this is entirely due to adsorbed acetone, not gas phase acetone. And so in this technique, when we flow acetone, we're measuring K-ad, all right? And so when we do desorption experiments, we turn the acetone gas flow off. And so our IR beam, once again, we're not going to see anything in the gas phase, but what we are going to see are molecules leaving the adsorbed phase, okay? So this is a look at some of our kinetics. So I'll describe this here. So we first establish a baseline spectrum by flowing 2 mass flow controllers at 50 cubic centimeter a minute. One is flowing through our mixing coil and being exhausted off to the hood. We do that so that we can maintain a nice steady concentration of volatile. And then we're only flowing pure nitrogen over to our drift cell. And so we use that as our sample spectrum, as well as our 0-minute spectrum. So this baseline that you see right here at 0 minutes, that's how we acquire this baseline spectrum. Okay, so then when we're ready to adsorb molecules, we flip over electronically our mass flow controller and our bypass valve, so that now we're only flowing 50 cubic centimeter of acetone over the surface. And we record spectrum in time ratioed to that original baseline spectrum. And as you can see, the carbonyl grows in here in this lovely Langmuir type adsorption. So here it is, it's going up and up and up, and then it achieves some type of equilibrium. And then we keep the same experiment going, and we switch it back into that baseline mode, which creates our desorption. And so now on this desorption graph, the spectrum that's at 0 minutes here was the spectrum at 63.2 minutes, but now we're no longer flowing acetone, so the peak decays, all right? So to be quantitative, we made 5 identical samples pictured right here with fairly identical characteristics. And we repeated this experiment over and over and over again. Routinely, sample number 2 did not show any adsorption. I have no idea why, but I would postulate that the surface was spoiled in some way. Perhaps it already has adsorbed something, okay? But consistently, sample 1, 3, 4, and 5 showed adsorption behavior such as this. And here, this is looking at the peak absorbance of that carbonyl over time. And you can see all of the samples have a different absolute absorbance that they saturate at. So sample 1 is saturating at about 2.5 times 10 to the minus 2 absorbance units, whereas sample 4 is significantly lower than that. However, when we normalize all of these samples to their max value, so in other words, for sample 1, this 2.5 times 10 minus 2, I normalize that, and that becomes 1.0. And so now all of this data, sample 1, 3, 4, and 5, all are on the same graph. And this is very cool. You can actually see that it's noisy, and that's to be expected because it's very difficult to be quantitative with IR. However, they're all showing the same type of behavior. So this is really cool. And so now based on that Langmuir adsorption, I came up with a kinetic model here that I'm not going to derive. But here you can see that e to the negative kt, that first order behavior. And all of these concentrations are normalized, just as I described, right? So for example, in the adsorption studies, our normalized equilibrium value is going to be 1.0. And you can see all of that right here. These are, individual fit parameters as well as a fit for the entire data set. And what's really cool about this, so we can extract rate constants. Okay, and so this is done individually for each sample and for all data. And even though there is some noise, the error of this rate constant fit is actually quite good. So I was really pleased by this. And you can see that reproducibly, the adsorption rate constant is greater than the desorption rate constant. And furthermore, you notice the desorption doesn't go down to 0, rather it goes down to something like 70%, meaning 70% of the acetone is still remaining after, something like 100 minutes. And also what's really cool, not shown in this presentation, but my student, Megan Wright, she was doing some of these experiments and then decided to close the drift cell and walked away and came back 24 hours later. And 24 hours later, she recorded a spectrum and it was still showing this 70% acetone coverage, which is really impressive when you think about it, because if you know anything about acetone, right, it evaporates if you look at it funny. And so the fact that 70% of it was still remaining stuck to the surface is a significant result. Okay, so I just looked, it's 2:45. I'm running thin on time here, so we're getting close to the end. So now we can add some other quantitative information on here, such as the equilibrium constant. So we can write the equilibrium constant as the ratio of the forward rate constant over the reverse rate constant, K add over K des. And that, of course, can also be related to the Gibbs free energy. And when we do that, we get a rate constant, or excuse me, an equilibrium constant that's greater than 1 and a free energy that's less than 0. And both of these parameters indicate that this adsorption will be spontaneous. Okay, so that's important. That's an important implication in the atmosphere. So I think that I've run out of time to really get into these qualitative studies. So I'm just going to kind of describe this very briefly. So in other experiments, when we've used a larger concentration of acetone, we don't see the adsorption or desorption behavior at all. We actually see a chemical reaction. So the way these experiments were done using a much larger acetone concentration, and we go through that adsorption behavior. And then when we flip the gas flow off and just do pure nitrogen gas flow over the surface, instead of seeing that carbonyl peak desorb, we see these very interesting and dynamic spectra. So we see chemistry. So here is the classic ALDOL condensation mechanism. And I'll just point out a few features of this mechanism. So we can see in the first steps, the production of water, right? Stable leaving group water. And you notice here in my spectrum early on, right? Look at this. We got this big whopper of a hydroxide asymmetric and symmetric stretching, right? And that's different than that dangling hydroxide spectrum. So it seems reasonable that this could be the production of water. All right. And also, as we go down the mechanism, we can see the creation of new carbon-carbon bonds, which we're going to see in this aliphatic region at 1477. And then as we keep going down the mechanism, we can see the creation of a new double bond, which we can see at this 1602. And so this macetyl oxide is, what we would expect for acetone plus acetone in the aldol condensation reaction. And it is confirmed that the double bond of this peak occurs around 1600 wave number. So that's pretty cool that we're seeing the creation of carbon-carbon bonds. And that's important to what we want to study here, okay? Because we're interested in this creation of some organic layer around the surface, right? And as these small molecules like acetone start landing and sticking, this is what's going to make them stick irreversibly, is going through this type of chemistry. So now, as I said, this is kind of like the classic textbook mechanism. So I've proposed a different initiation step based on the fact that this is not just simple acid catalyzed aldol condensation. So I believe that this could be happening through surface enol or surface enolate formation. And now once we make that enol, right, it's this double bond here that will be primed for creating new carbon-carbon bonds. That's how this oligomerization process is going to happen, okay? And if we were subscribing to the classic textbook chemistry, right, then perhaps our macetyl oxide could go on to become isoferrone. But what's important to note here is I'm not particularly interested in trying to find macetyl oxide or isoferrone out in the real environment. But what I am interested in is the creation of these higher molecular weight compounds that are going to form this layer around the surface, okay? So now, admittedly, we've had a hard time reproducing this type of chemistry. We don't know what our surface area is. Therefore, we don't know what our acetone coverage is. And this surface chemistry is highly dependent on the acetone coverage. So we've had a straightforward time reproducing the adsorption-desorption. It's been very difficult for us to reproduce this, okay? So conclusions here. So acetone does appear to stick to the TiO2 surface, and it seems reasonable that this is irreversible, meaning it could get transported long distances, okay? So our observations are fairly consistent with others. So others also do observe the formation of macetyl oxide, even though with this IR technique, it can be difficult to confirm directly that that is macetyl oxide, okay? So would we see a similar rate constant for different particle types? That's something that I'd like to explore in the future. And is adsorption, desorption kinetically competitive with other chemistry? And so what we mean by that is, for example, so using my determined adsorption rate constant converted into per second units, we could view that as about 2 × 10⁻³ 1/seconds for this adsorption process. If you look at, let's say, the reaction of acetone with the hydroxyl radical, and hydroxyl radical is a really important oxidizing agent in the atmosphere. It is one of the most common ways to remove organics from the atmosphere. So this will do a hydrogen atom abstraction on a methyl group and make water as a leaving group. And then, of course, we make an alkyl radical, and the chemistry goes crazy. It becomes, some type of secondary organic aerosol or even a semi-volatile organic compound. So you notice here that, of course, under pseudo first order conditions and assuming a 0.2 part per trillion OH concentration, this pseudo first order rate constant is 10,000 times slower than our adsorption. So where acetone is concerned, it would seem that this adsorption pathway is far more important than this hydroxyl chemistry. Now, of course, acetone and hydroxyl is not too famous. If we were thinking about something like isoprene or other terpenes, those are widely abundant in the atmosphere and they have double bonds. OH radicals and ozone react very fast at diffusion limited rates with double bonds, okay? So what we kind of want to do next is create our own particles with a mixture of environmental metal oxides. So really dilute down that titanium into more atmospherically relevant conditions. We'd like to expose the surface to other carbonyl compounds to see if this chemistry is common, if we can have a common expectation for carbonyls adsorbing to strong Lewis acids. So that's, that question, do we see the same chemistry? And then will those other VOCs also have kinetic competition with their loss via OH? Okay, so I'd like to acknowledge all the students that worked on this. So I've been working on this project for quite some time just because of how complicated it is. So Greg, John, Terry, Jesus, and Oscar were all responsible for building the apparatus and doing the initial testing on it. Emmy was my student who acquired that massive set of quantitative data. And then Megan and Natalie were involved in reproducing that data, the quantitative data. So Jesus got to present this work at SACNES in Honolulu a few years ago. And Megan presented this just last semester at the NCUR, the National Conference for Undergraduate Research. So thanks very much for your attention, and I'd be delighted to answer any questions.
All right. Thank you very much, Chris. Very interesting talk. We have time for a few questions from the audience.
Oh, yes. Okay, so Tesla, great question. Is it possible to use wildfire wood smoke particles as particle sources in the setup? Absolutely. We can put whatever we want in that drift cell. I suspect, however, when we start looking at organics, they're not going to have that same Lewis acid chemistry, right? So titanium does this really well because it's got that +4 oxidation state. So it's just a suck for electrons. I don't know that organics will do the same thing, but absolutely it is something that, so I forgot to mention, but Jacob Bagor is my newest student. And that's something that we're actually looking at. He's been looking at, or just starting to put organics as particles.
Do you think if you had an organic particle as your sample, you would have to use something besides acetone? I know it's a relatively, like compared to hydroxide, kind of a weak nucleophile.
Right. Well, so the point would be to do it with acetone, just so we have direct comparisons to the titanium studies. But yes, actually, just what Asia just said, carbon capture. Right. So we volatile organics will adsorb to carbon, right? But the mechanism will be different. So I don't expect that those oxygens will line up perfectly over those titaniums, which is what's facilitating that chemical reaction, right? That's why titanium is an excellent catalyst. And then, yeah, Jeff asks, titanium oxide is catalyst. Absolutely. So the reason why atmospheric chemists got interested in titanium is because all of the industrial chemists have known this about titanium for years. So they use titanium and iron and silicon of the like strong Lewis acids as these types of catalysts.
Chris, just a quick comment. In the past, I have worked a lot with carbon dots. And believe it or not, the interaction between those sort of nanodots or dots with oxygen is pretty strong, especially on the surface.
Right. are those pure carbon or are they some type of oxidized carbon?
Who knows what's there, right? So it should be a structure somehow similar to graphenes. So you have a lot of pi bonds and those pi systems,
Right.
and that will attract the
Yes.
oxygens and stuff.
Oh, that's actually a really excellent point. And so that right there, that could actually reveal a cool difference between what we call chemisorption versus physisorption, right? So perhaps the carbon particles you described would undergo physiadsorption through van der Waals interactions. Yeah, that's actually a really excellent point. So that confirms the direction for us to put organic particles in our chamber. And of course, this makes it relevant for also fire science, right? For seeing how smoke particles will pick up organics. Oh yes, beautiful question, Tesfa. I have written up 2 NSF grants trying to acquire a BET surface area analyzer, and I've been denied both times. So if anybody has a BET surface area analyzer lying around, that would be very useful for us to do those measurements. And then Jeff asked the pulse chase style experiment. Yeah, so that's what a lot of those experiments are in the literature, but you have to have a really fast technique to do it. It takes us 5 minutes just to acquire 1 IR spectrum. So we're seeing the true equilibrium with our IR technique. We're not seeing those quick exchanges.
All right, I think that's a good point to wrap up. Oh,
Well,
you wanna answer the the
Yeah.
final question?
yeah, we have department meeting starting in 1 minute, so we can keep talking then. So thanks everybody for coming. I'm glad that you all were interested, and that was a nice set of questions.
Thank you.
Thanks, Harmon.
Thank you. Thanks so much.